Yeah, good morning to all of you. In this session, I would like to demonstrate a small problem involving two heat exchangers connected in series. The purpose of these two heat exchangers is to heat water from 25 to 80 degrees centigrade. There are two possible hot streams available named as H1 and H2. H1 is available at 120 degrees centigrade, while H2 at 110. Both are at a pressure of 5 bar. Now the two heat exchangers which are connected in series will be able to pick up or use the hot stream 1 followed by hot stream 2 or hot stream 2 followed by hot stream 1. These are the two possible options we have, and we need to find out which one of these options is preferable and why. In addition to this, we would also like to find out what should be the intermediate temperature or the temperature between the two heat exchangers that minimizes the total area for both the sequences. In fact, you should be able to identify which one of these sequences or options are better based on some simple principles. Maybe even before simulation, you try to identify which one is better and try to establish whether the same result is obtained through simulation also. Now let me open a new simulation. So usually the first step in process simulation is to define all the components involved in your problem. So obviously in this problem, we have only one component that is being handled, which is water. So after defining the components involved in the problem, you can go to the next input screen by pressing N. So the second step is to choose a property model. In fact, you can see there are several property models available in Aspen, but in case of water or steam, the best bet is to use steam tables as the property model. So having chosen the property model, now you can go to the next input step by pressing N. So by default, when you open Aspen, you will be running property analysis. But now I would like to go to simulation environment. So you need to click on this and say OK. So this is the place where you will be able to draw your flow sheet, choose models and draw the flow sheet, complete the problem definition and so on. So different models available in Aspen are tabulated under different heads. So first of all, I would be using heat exchangers in this problem. So I go to this, I pick up a heat exchanger. Now, as I said, there are two possible options. In the first option, the first exchanger is taking heat from H1, followed by H2 in the second exchanger. Similarly, in the second option, the first exchanger will be picking up heat from H2, followed by H1 in the second exchanger. So I'll try to simulate both these options in the same problem. So I'll be using a manipulator known as a duplicator. The purpose of this duplicator is the input information given to this block will be copied onto all the outputs drawn from this particular block. So I'm taking one output and connecting it to the first option. Similarly, I can take another output from this block and connect it to the second option. So in other words, the moment you define stream 1, all that information will be automatically copied. The same information will be copied to both stream 2 as well as stream 5. In fact, you will be able to draw any number of output streams that you want using this duplicator block. Now, in addition to this, you can see there are utilities required to be defined for each heat exchanger. So let me also connect those inputs with respect to utilities, utility in and utility out for block B1. Similarly, utility in and utility out for block B2 in the first option. Similarly, the utility in and utility out for the block B3 followed by block B4. So we were able to define the problem, draw the flow sheet, right? Now we would like to simulate. Now you can see in order to simulate, the required input is incomplete. So we need to address some information with respect to streams as well as blocks. You don't have to worry what information is required. Simply press next it will automatically drive to the next input step that may be required for simulating this problem. Now you can see it is asking information with respect to material 1. So if you look at the main flow sheet, this is the input. According to rating models, we need to specify all the input streams along with equipment parameters. Then the simulator will be able to calculate the output streams or intermediate streams, right? So from the problem statement, you know these conditions. Cold water is available at 25 degrees centigrade and 1 bar with a flow rate of 1000 kg per hour. Remember, the number of degrees of freedom for a stream is C plus 2. Here there is only one component. So by defining 3 variables, we were able to satisfy the degrees of freedom. The moment you know these values, we should be in a position to calculate whatever is required, whatever property is required. In the same way, you can see some of these red dots need to be also addressed in order to complete the problem definition. So I'll press next. Now it is asking for stream 8. This happened to be the utility input to block B1, the first exchanger in option 1, which is taking, let us say, H1 followed by H2. Here, H2 followed by H1. So accordingly, I'll be defining this particular stream. So the hot stream 1 is available at 120, a pressure of 5 bar, and a flow rate of 1000 kg per hour as given in the problem statement. So we have satisfied this stream 8. Then go to the next input stream. Now it is asking information about stream 10, which is the utility input to the second exchanger. So let me also define this. Now the second utility, which is H2, is available at 110, 5 bar, and the same flow rate. Okay. Go to the next input stream. Now it is asking information about 12, that is the hot utility for the first exchanger in option 2. Now we are trying to use H2 followed by H1 because we have used it here H1 followed by H2. So accordingly, I'll be defining the input. H2 is available at 110, 5 bar, and a flow rate of 1000 kg per hour. So go to the next. Now you are required to specify H1, which is the hot utility input to the second exchanger in option 2, which is, let's say, 1000 kg per hour. So we have seen, you can see from the left side menu that we have addressed all the information required for the streams. We need to address information with respect to blocks in order to complete the problem definition. So again, you can press next to see what is the information that may be required. So we are required to specify some equipment parameters with respect to block B1, the first exchanger in option 1. I am choosing shortcut design. Remember, the shortcut design will be able to calculate the area of the exchanger given the heat transfer coefficient. In fact, I'm not going into these details, but you can see, given this heat transfer coefficient, it will be trying to calculate the overall area required. By default, Aspen will be using a constant value for the overall heat transfer coefficient, irrespective of the type of system that you are trying to handle. So in other words, this particular block will be able to calculate the area given the heat transfer coefficient. I'm using the default value for the time being. So I'm checking up, one of these specifications is mandatory. So I'm checking up cold stream outlet temperature. Remember, the cold stream is entering at 25. It has to be heated to some temperature below 80. And this is going to be fed into the second exchanger where it is going to be heated to 80. So temporarily, let me assume the temperature of the cold stream exit, cold stream outlet temperature in the first exchanger to be around 50. This is the temperature I'm looking at. So first of all, 25 to 50, this heating is done in the first exchanger. Then the remaining heating, 50 to 80, is done in the second exchanger. So you can see the required information for block B1 is complete. So go to the next input screen. So again, we are asked to provide information with respect to block B2. Again, the same design, but we know the outlet temperature from the second exchanger should be at 80 as per the problem statement. So go to the next input screen. Now it is asking information about block B3, that is the first exchanger in option 2. Again, let me assume the same outlet temperature of 50 so that we'll be able to compare these two options. Now, finally, the last exchanger, which is B4. Again, I'm choosing the same cold stream outlet temperature, a temperature of 80. Right? Now you can see all the red dots on the left-hand side have been addressed. So obviously you can see the required input is complete. So we should be in a position to run the problem. Say next. As you can see, you are ready to run. Say OK. Now you can see these blocks B1 to B5. B5 happen to be your duplicator block, are calculated only once, and you are able to get to the results without any warnings or errors. Of course, there are different ways of looking at your results. The first thing is, from the flow sheet, you can see 3 is the outlet temperature from B1, 4 is the outlet temperature from B2 in option 1, similarly 6 and 7 in option 2. So let me click on this stream summary and see whether we were able to get to those requirements. You can see 3 is at 50 and 6 is at 80, sorry, not 6, so 4 is at 80 and 6 is 50, 7 is 80. So we got to our results. Probably you can look at the remaining results available under the streams. This is not what we are interested for the time being. Now you can see what is happening. Let us try to analyze for this particular case. Now let me look at the results of the first exchanger. I'm interested in the area calculated. So the area calculated is something like this. So let me open calculator. So this is the area of the first exchanger in option 1 is calculated as 0.48608. Okay. Similarly, what is the area of the second exchanger? So this is about 1.36257. So this also I will add plus 1.36257. Now you can see the total area of these two exchangers is about 1.85. In order to heat water from 25 degrees centigrade to 50 in the first exchanger and 50 to 80, the total area required by option 1 happened to be about 1.85. So please remember this value so that we can compare it with the other option. Now let me go to the second option and try to look at the areas. So the area of the first exchanger in option 2 is 0.567269. Let me enter that value here. 0.567269. And similarly, what is the area of the second exchanger in option 2? This is 1.0215. Let me add this value to the first exchanger area. 1.0215. So this is about 1.6, 1.588, roughly about 1.6. What was the total area for option 1? 1.85, roughly. So why the total area is smaller in option 2 compared to option 1? The inlet and outlet temperatures are same. The intermediate temperature 50 is also similar, but option 2 is giving you a better result than option 1. So you can probably analyze why is it so. In addition to this particular problem, do you think we assumed 50? Do you think this 50 is an optimum temperature that is going to minimize the sum of these two areas? Do you think this temperature is going to influence the sum of these two areas? Of course, in both options. Now let us try to look at that as well. So in order to solve this problem, identify what is the effect of that intermediate temperature on the areas, I will be doing some sensitivity study. So click new. So it will be automatically opening it as sensitivity analysis 1. If you want, you can give your own name. So vary. What is that we are trying to vary? We are trying to vary the intermediate temperature or the temperature of the cold fluid that is coming from the exit of the first heat exchanger. So this is, all these are arranged in alphabetical order. You can probably go and see each one of them. You can see specified outlet temperature of cold stream. Initially, we have assumed this as 50. Now, I would like to see what is its effect on the sum of the two areas or the total areas of both the exchangers. Now, let me consider something like 30 to, let us say, 75 with an increment of 1 degree centigrade. So, I am varying now. This is what I am trying to do. 25 to 30 and 30 to 80. What is the total area? 25 to 31, 31 to 80. What is the total area? So like that, I would like to repeat these calculations, varying the temperature from 30 to 75 in steps of 1. What is that I am interested in observing? I would like to observe. So this is what I would like to see. I am interested in calculating or observing the areas of first exchanger and the area of the second exchanger. So let me name it. It is up to you to name this heat exchanger 1 in option 1 area. I have to define what it means. So it's a block variable. Block is B1, the first exchanger. Variable is area calculated. Similarly, I'll define heat exchanger 2 in option 1 area. So this is also a block variable. Block, of course, is the second one, B2. And variable is again area calculated. So these are the two values I'm interested in. So go to the next input screen. You need to tabulate your data. So you can simply press on these fill variables. So it will be listing out as a function of the temperature, what is the area of the first exchanger, what is the area of the second exchanger. But I can also find out what is the sum of these two areas, H11A plus H21A. I'll be able to find out what is the sum of the total areas of both the exchangers in option 1. Similarly, I would like to create another sensitivity for the second option. So again, the same problem. I am trying to vary the intermediate temperature, which is a block variable, and the variable, the block is now B3, that is the first exchanger in option 2, and the variable is T cold. Again, I would like to use the same range. It's up to you to vary these values and also choose appropriate increment depending on your convenience. I have defined, I have completed vary. Now I would like to define. Now I wanted to find out the area of the first exchanger in option 2. So I'm naming it as H12A. In the first option, I have defined this as H11A. The second subscript represents the option. The first subscript represents the number of heat exchangers. So it is also a block variable, similar to what we have done in the previous case. Block is B3, the first exchanger in option 2, and the variable is area calculated. Similarly, I would like to define another H22A. So this is also a block variable. Block is B4, variable is area calculated. Now go to the next input screen, fill variables. This is very much similar to the previous sensitivity analysis. H12A plus H22A. Having defined these sensitivities, now I would like to run the simulation. So you can see sensitivity 2 is involving blocks B3 and B4. Sensitivity 1 is involving blocks B1 and B2. How many times these blocks are calculated repeatedly? Because we said 30 to 75 in steps of 1. So 47 times these blocks are 47 and 47 times each sensitivity block is repeating these calculations. So S1 is repeating 47 times. That of course depends on the start value, end value, and the increment. Similarly, S2 also will be repeating the same number of times. Now we should be in a position to look at the results. Now from the results you can see when the intermediate temperature, the temperature in between the two exchangers is 30, the total area is 2.34. And as we keep on increasing this temperature, you can see the overall area is decreasing, the total area, not overall area. So it is decreasing up to some limit. Probably this is where there is a shift. Up to this, there is a decreasing trend, but from this point onwards, there is an increasing trend. Probably the optimum temperature is around 67. Of course, by reducing the increment, we may be able to exactly calculate what is the optimum temperature here. That minimizes the sum of the two areas. You will also be able to see these results in the form of a curve. I am interested in plotting the total area, not individual areas. So this is what is happening to the total area as you keep on increasing the temperature from 30 to 76 or 75, right? So you can see that the area is decreasing from 2.35 coming down to a minimum, and then once again it is showing an increasing trend. Probably the minimum may be around 66 and the area may be around 1.67, the total minimum area. Right? This is the case for option 1. And what about option 2? Again, you can see the same trend. Increasing the temperature is going to show a decreasing trend with respect to the total area. But one difference that you can observe in the case of sensitivity 1, when the outlet temperature from the first exchanger is 30, the total area was 2.35, whereas in the second case, the total area was 1.78. So this is giving the same result with a sum of areas lesser than the sum of areas in the first option. We have already observed with respect to an intermediate temperature of 50. Now, once again, you can observe here, there is a decreasing trend up to some time, probably here, and then showing an increasing trend. So the optimum temperature for the second case probably is somewhere around 50, where is it? 51 or 52 to 53, somewhere around it may lie, right? Again, you can see the results in the form of a plot for this second sensitivity. Now you can see when the temperature is 30, this is the total area, but it has come down to a value somewhere around 52 minimum value, which is slightly lower than 1.6, maybe about 1.58. Whereas this minimum area in the case of option 1 had been about 1.67. So you can see from these results that option 2 is giving you a better performance compared to option 1. Why do I say that? We were able to heat water from 25 to 80 using a smaller total area in option 2 compared to the total area required in option 1. Probably you can analyze why is it so, and is it in tune with your fundamental principles. Now, having done this far, I would also like to demonstrate one more tool. For the time being, let me delete these sensitivities so that they don't interfere with the other tool that I may be using. Both sensitivity blocks I am deleting. Now, can I find out what is the optimum temperature that minimizes the sum of these two areas? So I can use an optimization tool. It is also available under model analysis tools, optimization. Click on this, say new. By default, it names it as optimization 1. If you want, you can give your own name. Now, these are the things that you must be able to define in order to complete the definition required for optimization. What is defined? What is that you are trying to define here? The variables involved in objective function and constraints. What are the variables involved? I may be doing this optimization in option 1. If you are interested, you can also try that on option 2. So I would like to once again find out what is the area of the first exchanger. This is a block variable. Block is B1, variable is area calculated. Similarly, H21A, the area of the second exchanger in option 1. So this is also a block variable. Block is B2, variable is area calculated, right? So having defined the variables involved in the objective function, I can go to the next input. So I wanted to minimize the sum of these two areas, H11A plus H21A. right? Do you have any constraint in this problem? Already the problem definition is very clear. Water is getting heated from 25 to 80. So this temperature has to lie somewhere between 25 and 80, right? So there is no constraint. In fact, we'll be seeing some other problems later involving constraints. So go to the next input screen. So again, the areas of these two exchangers are going to be influenced by the intermediate temperature, which we have already observed in sensitivity block. So B1, the variable is T cold. We already have more or less the answer from sensitivity block, but you can also think of doing this. We know the solution is lying somewhere between 30 and 75, approximately at around 66. You should be able to get this value from sensitivity. We observed this, right? So I have completed the problem definition for optimization. The red dot has turned into blue tick. So we can run the simulation. Now you can see, because I am using optimization only in first option involving blocks B1 and B2, they are repeatedly calculated, maybe about 13 times, before which we came to a convergent solution. But the remaining blocks are calculated only once. If you have done a similar optimization study on B3 and B4, probably these B3 and B4 also will be iterated. Now you can observe the method that has been used to solve this optimization problem by default in Aspen has been SQP. It stands for Sequential Quadratic Programming. You can probably go through literature and identify how it optimizes any given problem. In fact, this method has been developed by one of the prominent professor of chemical engineering, Professor Bagler and his team in Carnegie Mellon University. And this method is especially suitable for solving optimization problems involved with simulation studies. Now let me look at the results. So the total minimum area actually has been found out. This is the objective function value, has been found out to be almost 1.67. We more or less got this result from sensitivity analysis also, right? But at what temperature we got this value? What is that we are manipulating? The exit temperature of cold fluid from the first exchanger. So we said the answer should lie somewhere between 30 and 75. So you can see the optimum temperature should be around 66.0423 in order to minimize the sum of these two areas. So the cold fluid should be heated from 25 to 66.02 or whatever value that was suggested here. And then the second heat exchanger should take care of the remaining heating. Then we are in a position to minimize the total area, right? So in the same way, if you can run the optimization problem on this second option, you will be able to calculate what temperature here will be able to minimize the total area of the two exchangers. So you also try to analyze why the second option is giving you a better performance, in what way this intermediate temperature is influencing the areas. So I will leave it to you to analyze this problem and satisfy yourself with the results of this simulation study. I would like to close down this recording